As you're kind of preparing to submit your homework one, some reminders. And again, these are kind of simple and small things, but please do pay attention because there's nothing worse than spending a lot of time on thinking about the homework problems, coming up with the solutions, and then not submitting in the right format and losing all points. Okay? So in particular, make sure you have been following all the homework policies. If for whatever reason it turns out it didn't, the better thing is not to submit rather than to get into trouble. Make sure your solutions are supposed to have separated out sections with a particular title, so that the proof idea is separate than proof details. Make sure you do that. We have provided you templates, so that should give you a place to start. But for example, if you're writing your solutions by hand, make sure you have the same kind of sections in your submission too. You have to submit your solutions in PDF. Word will not work. And also in PDF, you have to make sure it's not corrupted. So the first thing you should do after you submit is to make sure whether you yourself can preview your PDF on Autolab. If you cannot see your file on Autolab, neither can we. And if we can't see it, you get a 0 again. Okay. Other thing to note is your PDF cannot be bigger than 2 megabytes. So make sure that it's within that limit. Any questions on logistics of submitting homework one? Derek? Okay. Yeah, so if you are using Microsoft Word, make sure you store it as a PDF and then support it. Autolab will not be able to display Word. And if you notice in the template, it does say in bold, make sure you submit it as PDF. Any other questions? All right, so last time, at least at the end, we were kind of rushed, so I'll quickly go over the final proof of lemma 3 that we used to conclude that the output of the Gale-Shapley algorithm is always a stable matching. So we indeed did prove lemma 3, so we had proven that the output test is a perfect matching, and then we very quickly at the end proved that it has no instability. So I'll go over the proof of the no instability part with pictures, I guess. And so, as I said, the most common proof technique is proof by contradiction. Again, at a high level, you assume the negation of what you want to prove, and after some reasoning, you get a statement and its converse. Right? So you get a contradiction. And so the two observations we used was observation one was if a man gets engaged, he keeps on remain engaged throughout the course of the algorithm. And not only that, he keeps on getting engaged to better and better men. And for women, if a woman proposes to a man M prime first and then another man M, then she prefers M prime to M. So again, we'd prove it by contradiction. So we're going to assume that there is an instability. And so let's say this pair M comma W prime is something that's not paired up, and that's an instability. Again, this is an important part. While talking to some of you about even question one, there was confusion. An instability, for a pair to be an instability, the first thing it has to be the case is that they are not matched in the perfect match. Okay, if they are matched, then by definition, it's not an instability. Okay, so you look at a pair M comma W prime, that is not matched in the matching. So in this case, the matched pairs are the ones with the black edges. And it's an instability A if they're not paired up with each other, and they prefer each other to their current assigned partner. So M prefers W prime to W, and W prime prefers M to M prime. Now, the thing to note is if, again, this is the output of the algorithm. So if M is engaged to W prime, it has to be the case that M was the last man. Sorry. Oh, that's a typo. It should be W prime last proposed to M, not M prime. Sorry about that. All right, so we're going to do a case analysis and contradict either one of these two statements. So we're going to do a case analysis depending on whether M prime had proposed to M at some point or not. And so the first case is, let's assume W prime never ever proposed to M. However, note that W prime is currently assigned to M prime. That means she proposed to M prime, but she has never proposed to M. So that means by the second observation, it follows that W prime actually prefers M prime to M. Again, that's because she proposed to M prime but never proposed to M. Okay? And this is a contradiction because in the previous thing we assumed since M comma W prime was an instability, it had to be the case that W prime preferred M to M prime. Okay? And so this is our contradiction. So we are contradicting this fact. You probably don't even remember the run of the algorithm on the Firefly, but this was one of the examples that this would happen. So at the run of the Gale-Shapley algorithm where we looked at, Inara never proposed to Simon, and she only proposed to Mal. This doesn't work, but anyways. The second case is if W prime had at some point proposed to M. And we again look at two subcases. The first subcase is M actually had accepted M's proposal at that point of time. However, M is finally engaged to W. So at some point he was engaged to W prime because he accepted her proposal, but he's finally engaged to W. So by observation 1, this has to mean that M prefers W to W prime. And again, this contradicts our assumption that M actually prefers W prime to W. And again, here's an example. The other case was M actually had rejected W prime's proposal. And let's say the only reason that would have happened at that point of time was, say M was engaged to some other woman, double prime, who he preferred to W prime. And since he's finally engaged to W, it has to be the case that he prefers W to W double prime. And by transitivity of preference, since he prefers W to W double prime and W double prime to W prime, that means that he prefers W to W prime. But that again contradicts what's implied by M comma W prime being an instability, that M prefers W prime to W. So what we did was a case analysis based on whether W prime ever proposed to M. If not, we came up with a contradiction. If she did, we looked at the case for whether M accepted W prime's proposal or not. If it did, we came up with a contradiction. If he did not, he also came up with a contradiction. So basically, in all possible outcomes, we have come up with a contradiction. So we completely and finally contradict our assumption that M comma W prime was an instability. Okay? And so that completes the proof of lemma 3. That also completes the proof of correctness of the Gale-Shapley algorithm. Are there any questions? Maybe talk to your friends for half a minute. Let me know if any questions. If not, we'll move on. All right, are there any questions? Evan. Sorry?
Are you going to prove that the algorithm is deterministic?
So Evan's question was, am I going to prove that the algorithm is deterministic? You mean by that the algorithm always outputs the same stable matching? Hold on to your question for maybe 5 seconds or more, depending on if someone else has a question. Are there any other questions? All right. So here are kind of two natural questions. So I'll start off with the second one because that's more relevant to what Evan asked. So if you note that the way we have stated the algorithm, it is not quite deterministic. In the sense it says, if there exists a free woman, pick a free woman, right? It doesn't say pick which one. Right. Of course, if they have only one free woman, it's completely determined. But what if there's more? And it's plausible that if you pick different free women at different point of time, so you look at 2 different runs of the algorithms where you make different choices of which free woman you picked, maybe you will get a different stable matching at the end. Okay? So the absolutely cool thing that you can prove is that it doesn't matter. No matter how you choose the free woman in any iteration, as long as you're choosing one, the output of the Gale-Shapley algorithm is always going to be the same set of stable matching. Okay? So this shows that there is no way to get more than one stable matching out of Gale-Shapley if, say, only the women are doing the proposing. If all the men do the proposing, then you could potentially eke out another one stable matching, but that's pretty much it. Okay, so there's, at least the way things are stated, you cannot get more than 2 stable matchings. Okay. The other point is, and this was also noted and someone had asked a question, is something related to fairness. So if you look at the status of men at the end of each iteration, they keep on getting it better and better, right? So they keep on getting engaged to better and better women. Whereas for women, it's the opposite. They keep on getting engaged to worse and worse men. Right? And so you can start asking questions of whether this is the fairest thing you can do and things like that. And I won't tell you the answer. It's there. You can set up a notion of what is a fair, stable matching. And there is a notion of fairness under which the Gale-Shapley notion of the output of the Gale-Shapley algorithm satisfies that notion of fairness. Okay, the notion of fairness is not whether the men get the best possible woman that they can, or whether the women get the best possible men that they can, just based on the preference list. But it turns out there's a notion of fairness where you look across all possible stable matchings. And among these stable matchings, you can come up with a notion of fairness, and the Gale-Shapley algorithm is most fair among just these stable matchings. Okay? So what I'm saying is, if you look at myopically, it seems like it's not fair to the women because they keep on getting engaged to worse and worse men. But there is a notion of fairness where you look across all stable matchings, and it turns out that the women do get the fairest possible solution. Okay? I'm not going to cover either in class. These are great things to read up, and so these are all assigned as reading assignments. Okay, so any questions? Other questions on Gale-Shapley? Yeah, Evan.
You said that this was used to match residents to hospitals. So in that situation, who proposes first?
So Evan's question was, this is used to match hospitals, residents. In that case, who proposes? I actually do not know. And I think the algorithm is very slightly different from this, but I should know the answer. I'll make sure by next year I know, but okay. Any other questions? All right, so again, let's kind of go through the various steps that we have done over the last couple of weeks. So again, as a reminder, this is kind of the flow chart. You start off with the problem statement, which in this case was the problem of national resident matching program. Then you come up with, you formalize it. And sometimes you simplify it, like we did in this case where you assumed that the number of applicants is equal to the number of employers, which is not the case in the original national resident matching program. Then you want to design an algorithm, and almost always you should first start off with the brute force algorithm. First, make sure that you can solve the problem in finite time, and that typically would be exponential time. And then you want to come up with something that's more efficient. Okay? So you want to do the analysis of this algorithm, which has two parts. One is to analyze that the algorithm is correct. That is, no matter what the input is, the algorithm always outputs what it's supposed to, which we just finished. The other thing is you want to do a runtime analysis, and this is where typically you have to start paying much closer attention to what data structures you use. Because if you don't use the best possible data structures, then your runtime won't be as efficient as possible. Okay. So that's where we are going next. And so even before we start analyzing the runtime of Gale-Shapley algorithm, we're talking about efficient algorithms so far, right? But we are not really defined what it means, right? So I'll just go through a couple of reasonable sounding definitions, then argue why they are not reasonable, and then come up with the one that we are going to look in this course, and then maybe tell you why that might not also be reasonable, okay? But so one of the things that you would want your code to do is run fast in practice, right? So you can say your algorithm is efficient if when implemented it runs quickly, and you don't care about maybe worst cases, maybe on real instances, right? The problem, of course, is when you say implemented where, right? You know, are you implementing on your smartphone or a laptop or a supercomputer? And then, you know, the notions of efficiency can be different. And again, not that it's not important to try to optimize your code to run on the platform that you want to. It's just that mathematically it gets you get bogged down in details that are platform dependent. Okay? So to make our life easier in this course, we want a notion of efficiency that's platform independent. Okay? And the next question is, what are real instances? And this is a very, very tricky question to answer. But I mean, real for whom? Real when, right? You know, when computers came about, people were like, oh, anything with more than 100 inputs is not real, right? And that's clearly not the case, right? So what's real today might not be real 10 years down the line. And so we're just going to completely sidestep this issue by trying to argue that the algorithm should run fast on all inputs. So when we talk about efficiency, we're going to talk about what is the absolute worst runtime that this algorithm can have on all possible inputs. And again, it's not that this is the best possible way to solve it, but the point is, if you're guaranteed to run fast on all possible inputs, you will run fast on all possible inputs that your algorithm would actually see in practice, right? So it's a much stronger condition, but if you can achieve that, then that's good. And then the question is efficient. You say efficient, but efficient in terms of what? Right? What is your measure? What is the parameter that you're going to track? Okay. And it turns out that the correct way to look at is the input size that I'll denote by capital N just to differentiate it from little n. And so the input size you typically think of is if your, let's say your input is presented to you in an array, right? So let's say your preference list, each preference list is an array, okay? How many entries in the array do you need? So that's my notion of input. So if I talk about that, what is the input size for the stable matching problem where you have little n men and women? Kishan?
The 2n preference list.
There are 2n preference lists, but how large is it? How many elements do you need? How big is each preference list? Someone said 2n squared, and that is the right answer. So you have one preference list for each n men and each woman. So you have 2n preference lists. Each preference list has n elements in it. Right? So the worst case input size is 2n squared. Okay, so the input size here is not little n, but something that tracks like little n squared. Okay. I actually forgot to wear my t-shirt that says everything that I say in class will be on the exam. This question based on this observation is always there on the midterm. I tell every year the class that it's going to be the midterm, but still 50% students get it wrong. So remember this fact, for the stable matching problem, the input size is not little n, but something like little n squared, right? Because you have these two n preferences. All right. The other question you can talk about is we'll be talking about, brute force, which hopefully is something clear that is not efficient, right? And so we can say, well, maybe it's quantitatively or analytically better than brute force, right? But the reason this is, and so we all agree that n factorial is not a good term, right? So it's something we want to avoid in general. But when you say analytically or quantitatively better, what does it mean? I mean, will you be okay with a factor of 2? Probably not. I mean, n factorial over 2 is not going to buy you much, right? Is it 100? Still not clear, right? N factorial over 100, even for n equal to 20, is still a pretty darn big number. So the point that I'm trying to get across here is when you say it's quantitatively better, it has to be something that scales with the input size. Because you can't say it's just always 100x better. So here's the third definition, which informally says it should scale well with the input size. Okay? So not this, basically. So in particular, what we want to say is if the input size increases by a constant factor, say it doubles, then your runtime should also increase by a constant factor. It might not double. Maybe it increases by a factor of 4. But the point is, if your input size doubles, your runtime shouldn't be quadratically worse, say, for example. Right? And so now if you think about it, what I'm saying is, let's say I replace n by 2n, then my runtime should be such that I only get a constant factor out. So if you think about it for a while, this necessarily implies that your runtime should be what's known as polynomial runtime. What that means is there exists absolute constant C and D, so that the number of steps taken by your algorithm grows something like C times n to the d. So if you replace n by 2n, you're going to get an extra factor of 2 to the d. So if d is something like 2, that's a factor of 4. Okay? Now, of course, obviously you want d to be as small as possible, but at the very least, you should hope that if you double your input size, then your runtime doesn't grow by more than a constant factor. So the one thing that we'll not formally define, not because it's not something that should be done, but just because it then gets into details that we probably won't be looking that much into in this course. But the idea is every step would be something like a primitive computational step. Another way to think about this is think of any architecture, right? Any instruction that you can run in architecture would be one step. So like reading from memory, writing to memory. If you have two numbers in a register, then say adding them up. Okay, and things like that. These simple operations we'll think of as a primitive step. Okay. The question is this the only thing? No. I mean, you could start thinking about Boolean operations and say, that's my thing, and that's a perfectly valid thing to study, but it just makes our life more difficult if we go to that. Okay? So we're going to assume that storing, reading every element is constant time or takes one step. Doing simple operations on each of these elements like adding, multiplying is all constant time. Okay? There will be one or two times when this will not be true, but if that's the case, it will be clear, and I'll make sure that that's made clear. All right. So why is this nice? So I'll tell you why it's nice from my perspective, or like a mathematical perspective, like when you're trying to analyze problems. So one of the coolest things is if you start defining the notion of efficiency to be a polynomial runtime, then you can talk about whether a given problem is solvable efficiently or not. Whereas so the first thing to note is this, the fact that I'm saying that this constant C or this D, as long as it's some constant, I'm fine, takes care of the platform-dependent things. Right? So maybe a primitive step on your supercomputer would take much fewer number of cycles that would be much faster, but it won't be faster than some constant. So the idea here is, once we say we'll ignore kind of this big constant in front, we can essentially assume that our notion of efficiency should hold across all platforms. Now, this doesn't mean that the algorithm as is implemented the same way on all platforms will be equally efficient, and it won't. And so if you want to take an algorithm that we do in this class and try to optimize it for a certain platform, there will be a bunch of engineering that you need to do. Okay? But for the purpose of this course, we want to come up with a notion of efficiency that's kind of independent of platforms. And so once we have taken the platform out of context, like so we have kind of a abstract machine that we can run our algorithms on, you can start talking about whether the problem is easy to solve or not. Right? And not only that, and I mean, this I think is one of the coolest things in computer science. Not everyone might agree, but you can start talking about problems that are not efficient. Right? So once you have a notion of efficiency that's problem specific, you say a problem is efficient if there exists a polynomial time algorithm that solves it. And then you can also say a problem is not efficient if there does not exist any polynomial time algorithm to solve it. Okay. So there are a bunch of, I'm not going to spend a lot more on this. The book does a fairly good job in kind of introducing this notion of efficiency and giving more arguments than I did for why this is a good thing to look at. But now you guys basically have a bunch of reading assignments. So essentially, I think section 1.1 is also there because it includes the fairness stuff that we talked about. 1.1, 2.1, 2.2, 2.3. Any questions on notion of efficiency, polynomial runtime? Any objections?
What's your kid?
I forgot your name.
John?
John.
What's your kid's name?
What's my kid's name? Oh, this is Akash. Oh, that's easy to answer. I like easy questions. All right. Any other questions? And so again, I want to stress the notion of polynomial time being an efficient algorithm doesn't always work. Right? So there are many cases you come up with n squared. So even let's say n squared, which seems reasonable, right? The exponent is only 2. If your input size is like 1,000,000, you're just toast. That is not going to work. Right? So you, for example, and I did this, I think 2 years back, which was a bad thing to do. If you say you have an n cross n matrix, right? And you say, well, n squared is small, let me just try to allocate memory for this matrix, right? So I tried to allocate a 1,000,000 by 1,000,000 matrix, and it completely crashed the server. So I actually crashed Autolab once because I tried to do it. Right? So again, so what I'm trying to get across here is, don't think of polynomial time as being the final answer. Right? It's always the first cut. So you're trying to figure out, you want to solve a problem, can I solve it efficiently? So the first question is, can you at least solve it in polynomial time? So that's your first goal. You don't want a brute force exponential time algorithm to deal with. Once you have it down to polynomial time algorithm, then you can start to really narrow down. Ideally, you'd want something like linear. Right? So if you have 1,000,000 things, then an array of size 1,000,000 is okay. You can handle it. A matrix with 1,000,000 by 1,000,000 is bad. So, Evan.
That a problem has a solution, it can run in polynomial time without actually finding that solution.
So Evan's question is, can you ever show that there exists an algorithm that runs in a particular time, say in polynomial time, but do not explicitly give that algorithm? Mathematically, it's possible. I do not know of such a situation. However, There is one related work that that is along that question that you asked. So there exists an algorithm for a problem that we're going to look at in the course later on, which is guaranteed to have the best possible runtime, but I cannot tell you what the runtime is. So I can prove, or rather the authors have proved, that this is the absolute best runtime you can have, but they cannot give you a closed form expression that is n raised to whatever. They can say it's between this and this, but they can't tell you where it is. So weird things like that happen, but not that often, and definitely not for the problems we're going to consider in this course. Okay? And that's kind of the other argument for polynomial time, which I have not talked about, because again, in theory, you could have an algorithm that runs to the time n to the 1,000, right? And even for n equal to 2, you're toast. That algorithm is never going to run. But it so happens that you look at various algorithms, you rarely get these. The algorithms are much more well behaved. You start off with something like n cubed, n to the 4th, and so on and so forth. So, any other questions? Everyone okay with polynomial runtime? Okay, so we're going to next look at asymptotic analysis, which all of you have seen, I don't know how many times, 2 times, 3 times by now? At least 116 and 250 if you did both of the courses here. So I'm not going to belabor the point, but it turns out not everyone is super comfortable with asymptotic analysis, so we're going to spend like 1 lecture kind of quickly going over it. Yeah. All right, so what I plotted here on the x-axis is the size of the input. On the y-axis is the corresponding runtime. Right? So which one is the best runtime? Okay, which one is the worst runtime? Yellow, right? It's growing pretty quickly. Which one's better between red and blue? Blue, right. Not quite, so that was a trick question. So now if you see, the red seems to be worse. Right? Blue is still best. So note I've only gone from n equal to 8 to n equal to 10, and at this point in time you can't really tell the difference between yellow and blue. Okay? And so it turns out that this red guy is n factorial, which as we had talked is really, really bad. The yellow is 100 n squared, and the blue is n squared. Now, n squared is better than 100 n squared, but when you're in the same plot as n factorial, that factor of 100 doesn't matter. Okay? And in some sense, this is the essence. At the first cut, what we want to do with asymptotic analysis is, at the very least, we want to say something like n factorial is way worse than 100 n squared or n squared. And we don't really care about whether there's a factor of 100 there. So I said this is kind of like the asymptotic view of looking at things. And so you can, here's kind of a connection chart. You can think of big O as proving an upper bound. So saying, instead of saying a number is less than equal to, it's kind of big O, but you're fudging some constants here and there. So that's why I'm saying less than equal to is big O with glasses, greater than equal to is big omega, and equal to is theta. So how many of you have seen big O before? Okay, big omega. Okay, big theta. Okay. So for most of the course, we are going to look at big O, but we will look at omega and theta in this course. Or one of the students in 331, Alexandra, had this great doodle, which I think also does the job. So whatever helps you remember what big O, omega, and theta corresponds to is fine with me. Just pick one and make sure you remember the correspondence. All right, so informally or pictorially, when I say a function g of n is big O of f of n, what this means is if I plot g of n, then there will exist some number n naught. So that beyond that number, if you plot c times f of n, g of n always lies below. Now, note that I have not said that this c times f of n has to look like g. It doesn't matter. As long as c times f of n always stays above, I'm good. Right? If this happens, there exists some constant c and exists some constant n naught, then g of n is big O of f. If you want to do omega, it's the reverse. You want to bound it from below. So again, there exists some constant, say n1, so that epsilon times f always stays below g of n. And again, this can vary widely as long as it stays below you. Any questions on this? If you're worried that you didn't quite follow the definition of big O and omega, don't worry, we are going to look at it next. But are there any questions while I set up for the document camera? All right, this needs to focus.
There's like some stuff on the left. Yeah. So what I'm going to do is kind of quickly go over basically the definitions that we just looked at. We're just going to do some quick examples just to make sure everyone's on the same page. And then we're going to quickly go over some properties of this notations that we're going to use. Okay. So again, the big O notation, which is pronounced as I've written. So we say g of n is big O of f of n if there exists constant c and some number n naught
So that if you draw the curve out g of n, there exists some number n naught then c times f is always above g times n. So we're going to look at the expression 10n plus 1, and I'm just going to ask you some quick questions of whether this is big O of certain thing, and you say yes or no. Okay. All right. So is this big O of square root n? No. So I mean, you can put in large constants in front of square root n so that it's bigger than n, but after a certain value, n will start to go much faster than square root n. So this is not true. Is it big O of n? Yes, right? I mean, so for example, if instead of 10n, if we had 11n, then this is always less than or equal to 11n. Right? All right, so is this big O of n squared? Yes. Is this big O of n factorial? Yes. All right. So we're going to look at big omega notation. So we say g of n is omega f of n if there exists some constant epsilon and some constant n1 so that if you draw epsilon times f of n, it's always below this curve. So let's do the same exercise. So it's 10n plus 1 omega of square root n. Yes, so like n is always bigger than square root n. Right? So this is true. Is this omega n? Yes, right, because 10n plus 1 is always n. Is this omega n squared? No, because after a certain point of time, n squared will become 10n plus 1. Omega n factorial? No, right? I mean, n factorial goes faster than n squared. So this is not happening. Okay. So we next come to the big theta notation. So we say g of n is theta f of n if it's both omega f of n and big O of f of n. Okay. Sorry, is if one g of n is big O of f of n and g of n is omega f of n. So now if you draw the plot, so this is g of n, and so what this means is you have c times of f n be above g of n after a certain value, and so basically there will be a value, say n2, after which c of f of n is always above and epsilon of f of n is always below. So it's kind of these two curves sandwich the plot for g of n. Okay. All right, so let's go through all the examples. Is this theta of square root n? No, why not? Because it's not big O of square root n. It has to be both big O and. Is it theta of n? Yep. And it's again not theta of n squared and not theta of n factorial because they are not omegas of. Okay. All right. Any questions so far? So the book has a bit more formal definitions for all of these and had a bunch of properties about it in chapter 2, I believe. So please do and go ahead and read up on those. This is all I'm going to do to define this. So what I'm going to do next is talk about some properties which are fairly natural, and if you think about it, it's fairly easy to prove, but turn out to be incredibly useful when we are trying to do runtime analysis. Okay? So I'm just going to state 3 properties. So I'm going to state all of these properties in terms of big O, but they all hold for omega and theta. Okay? So these are also valid for omega and theta. So the first one is the transitive property, which says if g of n is big O of f of n and f of n is big O of h of n, then g of n is big O of h of n. So if g of n is big O of f of n and f of n is big O of h of n, then that implies g of n is big O of h of n. So for example, you can argue, or we just said that 10n plus 1 is big O of n. And it's not too hard to show that n is big O of n squared, because n is always less than or equal to n squared. And so these two implies 10n plus 1 is big O of n squared. And so for example, this argues this claim that we made earlier. All right, so the next one is what we'll call the additive property. So this says if f of n is big O of h of n and g of n is big O of h of n, then the sum of f and g is also big O of h. So that implies f of n plus g of n is big O of h of n. And so for example, it's fairly easy to argue that 10n is big O of n because 10n is never more than 10n. And 1 is big O of n. So that implies 10n plus 1 is big O of n. For example, we also had claimed earlier. Finally, we have the multiplicative property, which says if f of n is say big O of h1 of n and g of n is big O of h2 of n. So I'm saying f and g are both upper bounded by h1 and h2. So if you multiply f and g, you also multiply the upper bound. Okay? So then f of n times g of n is big O of h1n times h2. So as an example, it's kind of trivial, but let's say n is big O of n because, well, n is less than or equal to n. And 10 is big O of 1 because 10 is never more than 10 times 1. So that implies 10n is big O of n, which we just used over here. Okay. And it turns out for pretty much all of the runtime analysis that we're going to do, these are pretty much the only properties. I'm not saying that there will not be anything else that will ever get used, but these 3 are the most commonly used properties. Do you have any questions? All right, so I'll see you guys on Friday, and then we'll start analyzing algorithms.